So welcome to this masterclass from Cambridge Leadership College, and this masterclass is for students of AS level chemistry for this Cambridge International Exams exam board. So in this masterclass we're going to be going through a structured paper, paper 2, from the summer series in June 2015. And as usual with these masterclasses, we're going to reference quite heavily the comments that the examiners made after the students had completed the exam in 2015. And when the examiners make their comments, they make comments about each individual question, but also they provide some sort of overall or general comments. And the sort of summary or general comment that the examiners had about this paper was that compared to other papers for AS level chemistry, students generally did worse on this paper. And they thought about, why that was. And the sense was that this particular paper targets parts of the syllabus or parts of the curriculum that have been relatively poorly attended to by exams through previous year's papers. And so it's as if the examiners are looking through the specification of the syllabus and finding areas that haven't been usually attended to. So, for example, you might typically get questions on Le Chatelier's principle. That's a very, very common question in AS level chemistry exams. And that doesn't feature at all in this paper, but instead the examiners are looking to test students to make sure that areas that have been less frequently covered in previous exams have been properly revised and properly covered in this preparation that the students have done. So just watch out for that as we go through. It's a slightly different paper, I would say, and there's areas of knowledge which should be revised, but actually maybe have been neglected from previous exam preparation. And we get into that straight away, and the examiner was slightly shocked, I think, that this first question, 3 marks, was answered erratically by students, because really this is GCSE chemistry or even pre-GCSE chemistry. All you're being asked for here is the names of the particles that make up an atom. Of course, you know what they are. There's the, where's my pen? There's the neutron. There's the electron. And there's a proton. This is all really very, very familiar stuff, or should be to AS level candidates. And you know that the relative mass of the neutron and the proton, they have the same relative mass. The electron is much smaller. And the relative charge, well, 1 for the proton, 1 for the electron. You've got to have a negative there and a positive there. And the students lost marks if they didn't mark up these charges as positive or negative. So surprisingly, a lot of students didn't gain basically easy 3 marks in that first question. And that really should have been a nice, easy entrance to this paper with knowledge that should have been acquired well before AS level chemistry. So a bit of a surprise for the examiner there that the students didn't do so well on that. Now, going into now working about, on relative atomic mass. And again, you've got some simple definitions down here, again, for 3 marks. And the examiner said that lots of students didn't get full marks here, and it's just a question of learning these definitions, well, and also understanding those definitions as well. So under exam conditions, you can reliably write out the definitions for some of these basic concepts that underpin AS and A-level chemistry. And in particular, the examiner needed to see that when you answer these questions, that you're referring to atoms in each of these questions. The examiner was finding that students weren't properly referring to atoms, because the relative atomic mass is a comparison between the mass of atoms. But I think the thing is here that there's in the foundational early parts of an A level course or an AS level course, students are immediately hit with lots of definitions that superficially, to an untrained ear, if you like, sound equivalent or sound similar. But they all have their own particular definitions and need to be understood and distinguished between them. So not only should you be able to give a definition of relative atomic mass, but there's a lot of other similar definitions that you need to that you should discriminate between. So in addition to the relative atomic mass, you should be able to distinguish that between the relative isotopic mass and the relative molecular mass. Now you can see how all these things sound similar, but are in fact have very distinct and particular definitions. And closely related to that is the relative formula mass. Okay, these are all the relative masses that you should be familiar with. Another relative mass is the empirical formula mass. You should be able to distinguish that between a relative molecular mass and an empirical formula mass. You need to distinguish as well between all these different relative masses and the mass number. And you need to distinguish as well between all these different definitions here and molar mass. Now, I understand that it is a challenge, especially because all of these definitions come at the start of an AS level or A level course. But it's really, really very important that these are foundational concepts, and students really do have to know the definitions and understand the differences, for example, between relative isotopic mass and relative atomic mass, or the difference between the relative molecular mass and the empirical formula mass, and distinguish between the mass number and, for example, the molar mass. So these all have particular definitions, and the examiner is saying that it's well worth the investment in your time to make sure you've understood the differences between these and that you've learned them so that they can be used and written out under exam conditions. Okay, well, this next piece of work was relatively well understood by the students. Here's the mass spectrum. You've got to work out the relative atomic mass, and these are the mass charge ratios for each isotope for this particular element. And so to work out the relative atomic mass, well, it's the weighted mean of all these particular masses of isotopes. And so you've got to do a calculation of 0.89% times 74, which is that one there, isn't it? Plus 9.37% times 76, plus 7.63% times 77, and you go on until you've covered all the particular isotopes, and then divided by 100 because you're working percentages. And that gives you the relative atomic mass, because it's the weighted mean, isn't it, of all the masses of these particular isotopes of this particular element. And when you get that, you've done the calculation with, you've just worked through all the numbers in your calculator. You've got to give your answer, you see here, to 2 decimal places. Now you do have to watch this, because sometimes in these calculations they're asking for significant figures, sometimes they're asking for decimal places. And the number that you end up with on your calculator is 79.041, and of course, to make sure that's 2 decimal places, that's 79.041. 0.04. Don't get that confused with significant figures. That would be a very, very different answer. So you're putting in there this weighted mean according to the abundances of the mass of each different isotope. And once you've got the relative atomic mass, well, relative atomic mass is one of the values that you can look up in the data book of your periodic table. So you can look that up, and when you do that, you find that that relative atomic mass is given for the element selenium. Good. You're now going to use some of these relative atomic masses that you've been calculating. There's one of these other terms coming in here, isn't there? We saw earlier on, I wrote down all these definitions that you should know, and one of them was the relative formula mass and an empirical formula mass. And you're going to use both of those now to work on calculating a molecular formula for this chloride here. So you're given that this substance contains tellurium and chlorine. Now it's just talking about the mass of chlorine. So that's the chlorine, the element, not a diatomic chlorine molecule. The examiner noted that some students were doing that. And first of all, you need to write here the mass in 100 grams. We need to work with a mass, the mass in 100 grams. And if you've got 52.6% by mass, then in 100 grams, you would have 52.6 grams of chlorine. And to work out the mass of tellurium, you would have just subtract that, and you end up with a mass of 47.4 grams in 100 grams of this substance. Now, you now then need to look up the molar mass, which in this case is just the relative atomic mass expressed in units of grams per mole. You can read that off the periodic table. In the data book, there's a molar mass for chlorine atoms of 35.5 grams per mole, and you've got a molar mass for tellurium of 127.6 grams per mole. You can look up the relative atomic mass in the periodic table, and for the molar mass, you add the units of grams per mole. And to work out the amount, the number of moles, then you're using this expression, aren't you? So excuse me, that the number of moles, the amount, is equal to the mass, a little m, divided by the molar mass, a large M. Now we've got the mass there, because we worked out the mass in 100 grams, and we've got the molar mass, and if we divide the mass by the molar mass, then we get the amount, the number of moles, which is 1.482 and 715. Okay, now I've written that out to 4 significant figures. You don't want to round too early in these kinds of calculations. And that's the ratio, isn't it, of the amounts, the ratio about the number of moles. Now, that's a little awkward to deal with. So if you convert that to a ratio that's easier to visualize, now you divide by the smallest number here, divide that by itself, gives 1. And if you divide this 1.482 divided by 0.3715, then you end up with 3.98. Now, because we're working out a molecular formula, that will just have integer values for the relative number of atoms, and so we just need to round that up, and that's very close to, approximately close to, a 4-to-1 ratio of. Sorry, I've got this the wrong way around. I'm copying from my notes here. Excuse me. Oh, excuse me. I was copying from my notes and I got it the wrong way around for you there. So let me just start all that again. I'll just make sure I've got it correctly done in my notes. So that's the I had chlorine in my notes there and tellurium in my notes there. The mass for chlorine was 52.6. The mass for tellurium is 47.4. The molar mass for chlorine is 35.5 grams per mole. The molar mass for tellurium is 127.6 grams per mole. The amount of chlorine, and this is where I went wrong just now, is 1.482. The amount for tellurium is 0.3715. And so that's the ratio of the amounts. To get a ratio that's a bit easier to work with, we divide through by the smaller number here, and we get this ratio of 3.98 to 1, which is approximately 4 to 1. And so we've got a ratio, haven't we, of TeCl4, and we've worked out there the empirical formula. This kind of calculation gives us an empirical formula. And with the empirical formula, we can work out the empirical formula mass. Remember, that was one of the ones that I highlighted earlier? You've got empirical formula mass there. To get the empirical formula mass, we're just going to say, well, for tellurium, the relative atomic mass was 127.6, and we've got 4 of the relative atomic masses of chlorine, so that's 4 times 35.5. If you add that all together, then you get an empirical formula mass of 269.6. Now, you've got a relative formula mass of 270 and an empirical formula mass of 269.6. And what you should do is you should take your relative formula mass and divide it by your empirical formula mass. And you can see for us, we have 270 divided by 269.6. Well, that's pretty close to 1, isn't it? And that means that this empirical formula here, we don't need to change these subscripts at all. It's not like the actual molecular formula is Te2Cl8. We didn't need to multiply by 2, we just needed to multiply by 1. So we're just multiplying that empirical formula, the subscripts of the atoms, we're multiplying that by 1, and that gives us the molecular formula being identical to the empirical formula. And so the empirical formula, the molecular formula, is TeCl4. All right, so we've got this compound, TeCl4. It melts at a fairly low temperature, and it reacts with water. And you've got a state, that's a command word, the bonding and structure, and explain, that's another command word. All right, so you have to look out for these command words in these exams. So state, bonding and structure. Well, with a low melting point like that, the bonding is going to be covalent. That's the type of bonding. And the structure is simple molecular. And you've got to explain that. Well, it's got the low melting point. Because there's just weak intermolecular forces between molecules. And the other indicator here is that it reacts with water. So if it was ionic, it would dissolve in water, wouldn't it? But reaction suggests non-ionic, therefore covalent. Good. Now, this TeCl4, if you look that up in your data book, just checking my data book here, then tellurium is group 16. And you've got to try and suggest a reaction with that, with water. And you need this. Balance those up. So you'd have misty fumes of hydrogen chloride produced, and the tellurium oxide as another product. Okay, so this is again this is actually chemistry that should have been covered at GCSE actually. So looking at the reaction between sodium and chlorine to make sodium chloride, ionic substance. What would you see? Well, chlorine is a yellow-green gas, isn't it? Now, if that's going to be used up, one of the things that you'd see is a yellow-green gas color disappearing. The other thing that you'd see is when the sodium ion is reacting vigorously with chlorine, that will be burning with a typical orange color. Sodium gives orange colors when it burns. And when it burns in the yellow-green chlorine gas, then you'll see a white smoke. And that white smoke, of course, is the white sodium chloride that's being produced in the reaction between sodium and chlorine. So you've got 2 marks there. I think really for 2 marks you'd say, well, this is what you'd see. You'd see white smoke, and that's the sodium chloride being produced, and you'd see the typical orange flame as sodium burns. Now, if you're looking closely, you would see the yellow-green color of chlorine gas disappear. But the things that would stand out if you were just looking would be you'd say, oh, I saw a white smoke formed and there was an orange flame. If you looked carefully, you might have noticed that the yellow-green color of the chlorine gas had disappeared. So if I was in a hurry and looking for 2 marks, I would just be going for those 2 there. Those are the most evident things that you'd see as sodium burns in chlorine gas. Okay, so again, you've got to read these question stems quite carefully. So you've got a command word there, haven't you? Explain. And you've got to explain the differences in the melting point with reference to the structure and the bonding. And you need to refer to the electronegativity difference of the elements in your answer. So here you could see a large electronegativity difference between sodium and chlorine, and a small electronegativity difference between the silicon and chlorine. So, I mean, and actually the exam has been quite kind to you here, because the answer has been laid out so you properly address all the points in the question. So the structure for sodium chloride, of course, is a giant ionic lattice. Bonding, of course, ionic bonding. And for silicon chloride, you've got it's simple molecular with covalent bonds in the molecule, And between the molecules, you've got these dispersion forces or London forces. You've got dispersion forces between the molecules. And you could say, because we saw there was a small electronegativity difference between silicon and chlorine, you could say there are polar covalent bonds. And if you're thinking carefully, you've got these 4 polar covalent bonds, but overall, the molecule of silicon tetrachloride is non-polar, because these 4 polar bonds are arranged symmetrically in space, and so the polar bonds, when you do a vector addition, all cancel each other out, and the molecule overall is non-polar, even though the bonds themselves are slightly polar because of the electronegativity difference. And so that's why the intermolecular forces between silicon tetrachloride molecules are only dispersion forces, because the molecules themselves are non-polar. And so you've got to just then talk about the difference in the melting points. Well, the sodium chloride has this ionic bonding, or you could say has bonding of predominantly ionic character because of the large electronegativity difference. And so the NaCl has this high melting point because of this strong electrostatic force of attraction between the oppositely charged ions. And the silicon tetrachloride has a low melting point because there are only weak intermolecular forces between the discrete molecules. And there's only these dispersion forces because although the electronegativity difference gives the individual bonds a polarity, the molecule itself is overall nonpolar, and so there's only these weak dispersion forces in between the molecules, and that's the reason for the low melting point of silicon tetrachloride. Now, I think we started off this masterclass by noting that the examiner had said that students generally performed worse on this paper compared to previous years, and they thought one of the reasons for that was that the paper was addressing parts of the specification or parts of the syllabus that have been, over perhaps many years of exams, have been ignored slightly. And I think this work on gas laws is possibly one of those areas, because the students found this harder to do than you might have expected. And so we've got a graph here, and it's flagging up, isn't it, that probably we're going to have to use the ideal gas equation, and we need to talk about the differences between the real behavior of gases and the ideal behavior of gases. So it probably just helps us at the beginning of this section to remind ourselves of the kind of approximations that are made when you have the model of an ideal gas. Well, in an ideal gas, we're assuming, aren't we, that the gas particles are rigid spheres that undergo perfectly elastic collisions. We think these particles have no volume, and we think that these particles have no intermolecular forces. Now, we know that those are all approximations, but under conditions where the particles are far apart, then the volume of the particles relative to the volume of the gas is negligible. So it's not reasonable not unreasonable assumption to say that particles have no volume. And when the particles are moving fast, the collisions that they have are so energetic that the intermolecular forces between the particles are so weak in comparison that we can ignore them. And so, under conditions of where the volume is quite large, or where the particles are moving quite fast, actually kind of normal conditions for gases, I suppose, then this ideal model of a gas is a reasonable working model for considering how gases behave. But we've got a graph here showing that gases don't quite behave as an ideal gas. And we're plotting, aren't we, values of pressure and volume. And that tells us we're working with Boyle's law. Now, Boyle's law has this expression, that the pressure of a gas is proportional to the reciprocal of its volume. You could write that just as well by saying the volume of a gas is proportional to the reciprocal of its pressure. So a formal statement of Boyle's law would be to say that a fixed mass of a gas at a constant temperature has a volume that's inversely proportional to its pressure. So that one there. But these two expressions of Boyle's law are equivalent. And of course, the way to change a proportionality into an equality is to put in a constant. So it's true to say that if we had the proportionality, that's the same as saying it's a constant. Or you could rearrange that, just if I multiply both sides by v, that PV equals a constant. Okay? That's just another way of saying Boyle's law. And so for an ideal gas, PV equals a constant. It doesn't matter what the pressure is, PV is a constant. And so the line on the graph to show what the relationship should be for an ideal gas is PV equals a constant. And if PV is a constant, no matter what the pressure is, then PV is just a straight line, isn't it? PV is a constant. PV isn't changing, it's a constant. Okay? So you had to put on there the one line on the graph to show what the relationship should be for the same amount of an ideal gas. PV is a constant. That's Boyle's law for an ideal gas. And these lines here show gases that are departing from this ideal behavior. And that's where the question goes next. Well, we get a departure from ideal behavior at low temperatures, because at low temperatures the particles are moving slower, and so there's less energy in their collisions, and because the collisions are less energetic, then if there are intermolecular forces, then they can't be ignored anymore, because if the particles become close to each other and they're moving relatively slowly, then the energy of collision isn't so large that the intermolecular forces are insignificant. They start to become insignificant. So the lower the temperature, the greater the departure from this ideal behavior. Now, if you look at these lines here, well, which one is showing the biggest departure from this ideal behavior, this PV equals a constant? Okay. Well, it's pretty clear, isn't it, that this line here has got the greatest departure from the ideal gas behavior. And so T1 is at the lowest temperature. So you've got your two command words there, state and explain. T1 is lowest temperature. We had to do that. And the explanation is that you get the greatest deviation from ideal behavior at low temperatures. And then you have to do a further explanation here, don't you, with reference to intermolecular forces. And as the temperature goes down, the kinetic energy of the collisions goes down. And so the intermolecular forces of attraction start to become significant. And then you've got your command words here as well to state and explain the effective pressure and how the pressure change can affect, or let me just read that question. So, state and explain the effective pressure on the extent to which a gas deviates from ideal behavior. Well, we had up here, didn't we, that normally you can consider in an ideal gas that the gas particles have no volume, because compared to the volume of the gas itself, the actual size, the volume of the particles is insignificant. But if the volume gets smaller and smaller and smaller and smaller, eventually the actual volume of the gas particles starts to become significant relative to the volume of the gas. And so you get these small volumes at high pressures. And so the gas starts to deviate from ideal pressure, from ideal behavior when the pressure is high and the volume is small, and the volume of the gas, the volume of the particles relative to the volume of the gas starts to become significant. Okay, so let's do this next question in a little bit more detail, because the examiner flagged up that this was one that the students didn't work very well with. And I think, at least when I was working with this, I think what you've got to do is you've got to have some kind of strategy. You could dive in here and you could go wrong unless you've got a clearly thought out strategy of what you're trying to do. Well, the end game, what you're trying to get to, is the relative molecular mass, MR. Okay? Now, numerically, the relative molecular mass is the same as the molar mass. Numerically, they're the same. The relative molecular mass has no units. The molar mass has units of grams per mole. And the molar mass, well, that's rated by this expression, isn't it? That the amount, the number of moles, is equal to the mass divided by the molar mass. Or if you rearrange that, the molar mass is equal to the mass divided by the amount. So if we've got the mass and the amount, well, it looks like within the question here, there's something that's going to help us determine a mass. And because this question started off by looking at the ideal gas equation, then almost certainly we're going to need to be using PV equals nRT. Now in the question we had a pressure, didn't we? There it is. In the question we had a volume. There it is. The universal gas constant we can look up in the data book, and the temperature is given to us here, isn't it? Okay, so well, if you substitute in for the amount here, then you've got pressure times the volume is equal to the mass divided by the molar mass times RT, and we're trying to find this molar mass, aren't we? Because that's numerically the same as the relative molecular mass. And so the molar mass is going to be equal to the pressure, it's going to be equal to the mass times the gas constant times the temperature divided by the pressure divided by the volume. Okay, so that's our strategy. We're trying to get a molar mass which is numerically identical to the relative molecular mass. So let's just put that down there for the moment. The molar mass is equal to the mass times the gas constant times the temperature, that's in Kelvin, times the pressure times the volume. Let me just clean up the rest of that. But you can see once you've worked out your strategy, how you can get there. Now, your mass there is the mass of Y. Now we've got to work that out in a rather indirect way. Your first job is to work out the mass of air, because the flask was containing air when the first mass measurement was made. And you can work out the mass of air because you know that density is mass divided by volume. So the mass of air is going to be the density of air times the volume. And you had that value there. So you can work out the mass of air. If you know the mass of air, then you can work out the mass of the flask. You can just work that out by difference. And if you know the mass of the flask, then you can work out the mass of the gas, Y. So there's a little bit of tricky work there to work out the mass of the gas. Once you've got the mass of Y, you're almost ready to go, aren't you? Because the temperature is given, you've got to convert that to Kelvin, so you've got to add 273 to 26 to give you the temperature in Kelvin. The value of R you can look up in the data book. The pressure, it's given that to us in SI units there, so that can just be substituted in. And the last thing that you've got to watch is that the volume, of course, in the universal gas equation is represented by the unit of meters cubed. So you've got to convert 100 centimeters cubed to a meter cube value. And you know that 1 meter is the same as 0. Oh, sorry. Let me just get that right for you. That 1 centimeter is 0.01 meters, or rather, that's 1 times 10 to the minus 2 meters, isn't it? So 1 centimeter cubed is the same as 1 times 10 to the minus 6 meters cubed. And that's how you can convert from centimeters cubed to meters cubed, because you're going to have to substitute in this equation using meters cubed. So you've got to work through all of that, and you end up with a result of, when I did this, 43.989 grams per mole for the molar mass, and so that gives you 43.989 as a relative value for the relative molecular mass. Now, you just need to check back to the question, and the smallest number of significant figures that you're getting in the question was 3, wasn't it, there? We'll have to assume that's 3 significant figures as well. And so really, you should be giving your answer to the smallest number of significant figures that you had in the question, which was 3. And so a good answer for there to 3 significant figures would be 44.0. And just to be absolutely clear for the examiner, you can write 3 significant figures. Okay. Continuing on here, nitrogen, of course, has a very, very high bond enthalpy in the molecule, has a triple bond, and that's why nitrogen is so unreactive. You need a lot of energy to break that triple bond so that the new compounds can form. But you can react nitrogen inside a car engine, and the examiner is just looking there in that question to say that you have a very high temperature in the car engine. And there's a mark here for saying how the nitrogen monoxide, which is formed from the nitrogen in the car engine, is removed in a catalytic converter. Well, this is one of these sort of niche or sort of corner areas of the syllabus about catalytic converters, and it's part of the character of this paper that the examiners are testing areas of the syllabus that have been kind of left alone or ignored in previous exams. So that the point of the catalytic converter is that in the car engine, although you want the hydrocarbon, the petrol that is burned, to be completely combusted, complete combustion to carbon dioxide and water, in fact you get incomplete combustion, and you get some carbon left over, you get some carbon monoxide left over, and you're getting this nitrogen monoxide created when the high temperature of the car engine is allowing the nitrogen gas in the atmosphere and the oxygen gas in the atmosphere to combine to form nitrogen monoxide. And so the catalytic converter is going through a process to get rid of all of these, either the particulate carbon or the poisonous carbon monoxide or the nitrogen monoxide, which causes respiratory problems and can cause, as we see later in the question, acid rain as well. And so the catalytic converter, the equation that the examiner was looking for, was the catalytic converter can get rid of both the carbon monoxide and the nitrogen monoxide in a reaction which regenerates the nitrogen and produces the carbon dioxide, which is the intended product of complete combustion. So that's a good equation for showing how the nitrogen monoxide is removed back to nitrogen gas by the action of the catalytic converter. Now, we said that these nitrogen oxides have health impacts, but they also contribute to acid rain. And you had to have an equation here to show this nitrogen dioxide forming nitric acid in the atmosphere. Well, when you look at that, there's an oxidation process going on here. So you could imagine that at least on this side of the equation, you'd need some atmospheric oxygen. And you're getting a source of hydrogen atoms here. Well, what are you going to use in the atmosphere as a source of hydrogen atoms? That is the reactants in the equation that you're going to need to produce nitric acid. Now, once you've got your simple equation down, one of the things the examiner keeps asking students to pay attention to is to make sure that you balance these simple equations. And sometimes they look harder to balance than they should do. And there's a technique that you can use where you start your balancing operation by looking at the atoms of the element that appear least in the products. Now, that means I'm not going to start with oxygen here. Let's start with nitrogen. So if I look there and there, that's all balanced up, isn't it? So the next one I can move to is hydrogen. Well, there's one hydrogen atom on the right, two on the left, so I'm going to need two of those. And as soon as I do that, I've multiplied up the number of nitrogen atoms. So I've lost my balance for the nitrogen atoms. I can have two of those. Now, you can see here that I've now got, let's see, 1, 2, that's 6 oxygen atoms, 7 oxygen atoms on the left, and I've got 6 on the right, so I need more on the right over here. I could put 3 there, couldn't I? And that would give me 9 oxygen atoms. But bear in mind that I've got H2 over here. So that means I'm always going to need an even number of hydrogen atoms. So probably having a 3 there isn't a very good idea. Let's step up once more to 4 hydrogen atoms. Well, that would mean 2 of those. I've now got 4 nitrogen atoms, so I need 4 of those. And do a quick check now. I've got 4 nitrogens, 4 nitrogens, 4 hydrogens, 4 hydrogens, and that's 12 oxygens overall. I've got 2 there, 8 there, that's 10, and 2 there, it's 12. So that's balanced. So you see that I did that by identifying atoms of elements on the right-hand side of the equation that appear the least, and starting with those to start to balance up my equation. And that's one way in to doing these kind of balancing of symbol equations that you have to do whenever you quote a symbol equations. Okay, again, this is just another real detailed part of the specification or the syllabus that you'd have to learn. And I guess the message, if there had to be one from this overall exam, is that you need to do really very detailed revision of all aspects of the syllabus, because there's these little just single or double symbol equations that are being tested here. And you're looking at the catalytic role of nitrogen monoxide in the oxidation of sulfur dioxide. Well, if we didn't know that equation, well, we know that's happening because it's the oxidation of sodium dioxide to sodium trioxide. So that's definitely going to be happening. And you've got, I'm just going to actually put that up on the second row here. You'll see why in a moment. So you've got sulfur dioxide going to sulfur trioxide. And that's happening because the nitrogen monoxide initially reacts with some oxygen from an oxygen molecule. That makes nitrogen dioxide. The nitrogen dioxide goes on further to react with the sulfur dioxide, oxidizing it up to sulfur trioxide and producing, as one of the products, nitrogen dioxide. And if you see, the reactant that we started with there has been regenerated there through this intermediate nitrogen dioxide. And it's that regeneration that allows the nitrogen monoxide to have a catalytic role. It's not being used up in this process, it's being consumed and then regenerated. And so it's taking the role of a catalyst in the oxidation of sulfur dioxide. Good, all right, so now looking at this reaction here, we've got an aldehyde and we've got hydrogen cyanide, and we've got a small amount, and your radar should be up and running there. When you're talking about a small amount, that's possibly an indicator that this is acting as a catalyst. Okay, so just even that little part in the question stem should be planting a seed in your mind that later on you may have to think about sodium cyanide as a catalyst somehow in this process. Now, really some quite easy marks, 3 easy marks to work out the enthalpy change for this reaction. You've got this methanal, haven't you here? And it's reacting with hydrogen cyanide. I'm just drawing out these, they're not completely displayed structures, but they're close. And that's producing that, isn't it? And just to be completely clear, I'm just going to put that bond in as well. Okay. Now, you need to look here and see which bonds are broken and which bonds are formed in this reaction. So this is bonds broken, and this is bonds formed. and on the product side. Now, one of the things the examiner picked up was that some students went and in their calculation included the breaking of the carbon-hydrogen bonds there and the forming of the carbon-hydrogen bonds there. Well, you don't need to do that because, for one, in this particular mechanism, those bonds certainly don't get broken or formed. And anyway, as you did the calculation, the value here would be cancelled out by the value there. So it's not necessary to consider those bonds there. But it is necessary to consider that we're breaking that bond there, aren't we? And we're breaking that bond there. So we're breaking a carbonyl and we're breaking a hydrogen joined to a carbon atom. And on this side, we're making that bond there, aren't we? Which is a carbon-oxygen bond. And we're making that bond there, which is a oxygen-hydrogen bond. And we're making that bond there, which is a carbon-carbon bond. Now, you need to look up in the data book the value for these bond enthalpies, and they're all averages, aren't they? Because these are the ones in the data book are averages of carbon-hydrogen bonds in many different molecules, or oxygen-hydrogen bonds in many different molecules. So you're looking at these average bond enthalpies, and if you look up the average bond enthalpy for carbon double bonded to oxygen, that's 740 kilojoules per mole. For hydrogen bonded to carbon, that's 410 kilojoules per mole. For carbon singly bonded to oxygen, that's 360 kilojoules per mole, 460 kilojoules per mole, and 350 kilojoules per mole for the carbon-carbon bond. And so what you do is you add up the total for the bonds that were broken, which was 1,150, and the total energy given out, because this is an endothermic process here, bond breaking. This is an exothermic process here, bond forming. So that's 1170. And then you subtract the bonds that were formed from the bonds that were broken over here. And that gives you 1,170 minus 1,150, and that gives you an answer of 20 kilojoules per mole, and you must make sure that you have the negative value in front of that. Okay, so this is it. Again, an interesting part of the paper, because again, the examiner is working with you to look at how well you've learned definitions. So these are just definitions that you can look up in your revision guide or your textbook. So that I'll just leave you to look up those. And then you know that optical isomers are one kind of stereoisomer. There's geometrical isomers and optical isomers. There's the two kinds of stereoisomers. And these optical isomers each have a chiral center. And you've got to suggest why there's two optical isomers, or two enantiomers, another word for that, are produced in equal amounts by this reaction. And you have to say that this carbonyl group here is planar. And so the mechanism can have the nucleophilic attack by the hydrogen cyanide either from above or below. And there will be an equal number of nucleophilic attacks from above and below. And the attack from above will give one optical isomer, and the attack from below will give a different optical isomer, the two enantiomers. And so those ideas have got to come into the answer here, that you're talking about a planar carbonyl bond being attacked by a nucleophile equally from above and below, giving rise to the two optical isomers. Now, the thing to note at this point as well, and it's common again and again and again in many of these papers, is that Mechanisms, questions about mechanisms are mark-rich. Now, compared to other questions that we've seen so far, look here, you've got 5 marks. And that's because the examiner is going to be giving marks for charges, partial charges, lone pairs, curly arrows. Now, if you just imagine the mark scheme is 1 mark for that, 1 mark for that, 1 mark from that, 1 mark for that, you can quickly see how we accrue 5 marks. And so as part of your learning strategy, your revision strategy, your exam preparation, learning and understanding mechanisms is a valuable investment because the mechanism questions are mark-rich. You're going to get a good return on the investment that you put in for working on mechanisms as part of your exam preparation. Well, let's start off then. So here's the carbonyl, and with the carbonyls, you always have electronegativity difference, where the oxygen is more electronegative than the carbon, and so electrons are drawn towards the oxygen atom away from the carbon. So that's given our 1 mark for partial charges. And then you've got to have lone pairs. Well, you need to add in a lone pair on the carbon atom as part of that nucleophile there. So that nucleophile then can undergo nucleophilic attack on the carbonyl, and you need to show the curly arrow from the lone pair to the carbon where the new bond is going to be formed. So from the lone pair to the carbon. And so you end up with then the intermediate here, where the nitrile group is added on there, and you had a bond pair of electrons moving from the bond to become resident on the oxygen atom. So the oxygen atom now has a negative charge, and nothing has happened to that hydrogen there. Okay. Now, they've drawn in, remember this was sodium cyanide plus hydrogen cyanide. And so you're now going to get a further reaction between a lone pair that's there to form a bond with the hydrogen atom, because we're making the hydroxide group over here. So that lone pair is going there, isn't it? Just as we had here a lone pair going towards the carbon atom, here you've got a lone pair going towards the hydrogen atom. You're drawing a curly arrow from a lone pair to an atom. And then, just as we had here, a bond pair with a curly arrow showing movement to the target atom there. So that's a curly arrow there onto the carbon atom. Yes? And that gives us the result here. You've got an alcohol group here. And you can see as well that at that point you've regenerated, haven't you, the cyanide ion that you first started with. And if you start with a reactant here and you regenerate it as one of the products, then that's the classic description of catalytic activity, that a reactant isn't being used up in this case because it's being regenerated here. So with reference to your mechanism, explain the role of the sodium cyanide. Well, that's Cn minus Na, isn't it? So that's the cyanide ion. So the cyanide ion is regenerated. So it's acting as a catalyst. Okay, well, I suppose we're now moving into more familiar territory as well. I think this exam has targeted areas that have been relatively ignored in previous exams, but this work on isomers is pretty familiar territory. So you've got 4 alcohols, and they all have the same molecular formula. There it is, C4H10O. But they are all different structural isomers. All right. So just in your mind's eye, you've got the topic of isomers, and you can either have structural isomers or the one we just looked at in the previous question, stereoisomers. And the stereoisomers we saw have the same molecular formula and have atoms bonded in the same, each atom is bonded in the different isomers to the same atom as it is in all the other isomers. But the stereoisomers just have the bonds spatially arranged differently. So there's a different spatial arrangement of the bonds. But in the structural formulas, sorry, in the structural isomers, the atoms are actually all bonded to different partner atoms. And so the different type of structural isomers that you can have are chain isomers, where you might get a different carbon chain, but the same molecular formula. You can have positional isomers, so that's where you have the carbon chain is the same, maybe 4 carbons long, a bute chain, but the position of the functional group has changed. So you might have an alcohol on carbon number 1 in one isomer and the alcohol group on carbon number 2 in a different isomer. That would be a positional isomer. And finally, you can have functional group isomers, where you might have the same molecular formula, but actually when you drew out the displayed formula or the structural formula, you can see there's a different functional group and very different chemical behavior. But we know that in this question, they're all alcohols. They're 4 alcohols. And so we won't have any functional group isomerism because they all have the OH group. So we just need to be looking in these isomers for variations in their carbon chain and the position of the alcohol group, a positional isomer. So that's just our hierarchy of isomers that you should know, and that just helps you as your way in to this question. Now, as the question proceeds, they ask you to draw skeletal formulae. And so when I worked on this question, I found it easy to draw a kind of displayed formula before I tried to draw a skeletal formula. So you've got the molecular formula here, and you know it's an alcohol. And if you start drawing up some candidates, then you end up with the different possibilities a bit like this. So you could have, I'm not drawing in the hydrogens at the moment, so 4 carbons in a chain, and that's the easiest one to think of, isn't it? And then you could have this one. Okay, and that would be a chain isomer, wouldn't it? Because the carbon chain here is 4 carbons long, and here is 3 carbons long. So it's a kind of chain isomer. And then you could have one like that, and then comparing that one and that one there, the position of the alcohol group has moved from the number 1 carbon to the number 2 carbon. So that's a positional isomer. It's got the same carbon chain, 4 carbons in a row, but the position of the OH group has moved. And then finally, you've got this possibility. Remember that I'm not drawing in the hydrogens there. And that is another kind of chain isomer, isn't it? Because we've got a slightly different carbon chain here than we had here. And that one is a primary alcohol. That one is a primary alcohol. That's a secondary alcohol, and that's a tertiary alcohol. All right, so we've drawn them out. Now, in the question, it talks about these alcohols reacting with chromate 7, which is an oxidizing agent. And you need to know that primary alcohols can be oxidized to aldehydes. Secondary alcohols can be oxidized to ketones, but tertiary alcohols can't be oxidized at all. And so there's a clue here that alcohol A is not oxidized. So we know immediately that this one here is A. Now, what other clues have we got? It then talks about the reaction with hot concentrated sulfuric acid. And that reaction with alcohols is a dehydration reaction to form an alkene. You got, that's the, if you knew the homologous, the formula for the homologous series of alkenes, CnH2n, you can see we're getting an alkene there. And so with sulfuric acid, then that would be the alkene there. For this one, that would be the alkene, wouldn't it? Now this one and this one doesn't. Hang on. This one here could be going to that. If the dehydration happened that way, but if the dehydration happened that way, then you'd get that, wouldn't you? And for this one here, the dehydration, you would then get this for me. Okay, if we did it the other way, it's identical. All right, so those are the products of dehydration, and it says here that B gives a mixture of structural isomers, and so the only one that gave a mixture of structural isomers well, is this one here, isn't it? And we can look later on, because one of these is going to show a geometrical isomerism, which is one form of stereoisomerism. So that's A and B, and there's nothing in the question here to help us distinguish between that and that. And so when I did this, I had this one as D and this one as C. But actually, in the question, you could have had those the other way around, and the examiner, you can have either of those, C and D or D and C. So I've drawn out, haven't I, these kind of displayed formulas. To be a fully displayed formula, I should be adding in the hydrogens. I haven't done that just for convenience at the moment. But it also means that when I come on to draw the skeletal formula, the skeletal formula removes the hydrogens and just shows the carbon backbone. So this kind of view is a stepping stone to drawing the skeletal formula. So for example, if I had to draw the skeletal formula of that, I'm going 1, 2, 3, 4, OH. Yes? And the skeletal formula for this one down here would be 1, 2, 3, OH. Yeah, so it's quite a small step to go from this kind of view, just drawing the carbons, to the skeletal formula. And if you do that, and you put them into the various boxes down here, you get the skeletal formula of A, which was that, this one here. And the skeletal formulas for B, which was that, wasn't it? So if I just do B there, so that's 1, 1, 2, 3, 4 with an alcohol group there. 1, 2, 3, 4. Yep. One. So like this. 1, 2, 3, 4. What was I doing up here? 1, 2, 3, 4. So my mistake. You see how easy it is to get these skeletal formula wrong. Okay, there you go. So there's the skeletal formula and OH. You have to be very careful with this skeletal formula. They're quite easy to get wrong. And then C, what was my C? That was the straight chain. 1, 2, 3, 4. Yeah, I've got that. Here we go. 1, 2, 3, 4. And the alcohol group there. And then for D, you have that there. Okay. Now, and again, it's easier to check back to these kind of stepping stone formula up here before we get to the skeletal formula. And for A and B, well, they just, there's no difference between them. There's certainly no, they're not functional group isomers, are they? They are chain isomers. They just differ, don't they, in the carbon chain. These two, that's butan 2-ol, that's butan 1-ol, so that's position isomerism, and these two is just the position of the OH hasn't changed, but the nature of the carbon chain has. So those are chain isomers or chain isomerism. And then up here we had the two isomers, didn't we, that we got from B, and that is, well, I mean, you're working out the names, you have a stem, suffix, and prefix if you need it. So the stem here is for 4, it's but, and it's ene, and that would be but 1-ene, and the other one would be but 2-ene. So your naming conventions there are but 1-ene and but 2-ene, so those go in there. And one of these is showing stereoisomerism, and you have to draw it up here in the displayed formula. And the displayed formula shows all the atoms and all the bonds. So you may be tempted to write CH3 up here, and the examiner won't give you the marks for that. You've got to make sure you display all the bonds. So every single carbon-hydrogen bond, same down here, every single carbon-hydrogen bond, get all the hydrogens in there and there. That's the one isomer, it's trans, isn't it? And then the other stereoisomer, these are geometric stereoisomers. You've got these CH3 groups on the same side of the double bond, and no rotation is allowed around that double bond. And so these two methyl groups are on the same side, and the two methyl groups on the here are on the other side, and there's no rotation about the double bond, because that would require the breaking of a pi bond overlap between the two carbon atoms. Okay, so that's the end of our paper for this masterclass. You know, I think it's a really very, very instructive paper for students to do, because it's addressing these areas of the specification that can get relatively ignored, and some little equations that show you just how detailed you have to be in your exam preparation. It's also showing us that it's really, really worth the time to learn mechanisms carefully, because once those are done carefully, those mechanism questions are mark-rich questions, and it's a way for students to gain a lot of marks with their good understanding of mechanisms. So thank you for joining this masterclass. If there's questions that you have about this paper or any other papers that we've done, then the Z coaches will be delighted to follow up with you on the Slack channel. So put your questions there. And it just remains for me to say, wish you every success in your studies for AS level chemistry with Cambridge International Exams.